At the level of fundamental physics, the equations that govern particles are beautifully symmetric. If you film two atoms colliding and then play the film backward, the reversed motion still obeys the laws of mechanics or quantum theory. Nothing in those equations singles out a preferred direction of time. In this microscopic world, the future and the past are interchangeable, and processes can, in principle, run forward or backward. Doesn't it seem strange that nature's deepest rules are timeless, even though our experience is nothing but time-bound? At the human scale, reality feels entirely different. Drop a glass and it shatters irreversibly. No amount of waiting will make the shards leap back together. A person grows older with each day, never younger. Heat flows from hot coffee into the cold air, but never the other way around. This one-way direction, called the arrow of time, defines our lives and our memories. Yet it has no origin in the microscopic equations themselves. Where then does this arrow come from? The key lies in probability and statistics. While it is not forbidden by physics for shards to spontaneously reassemble into a glass, the number of ways for molecules to be arranged in a broken state vastly outnumbers the ways to be arranged in an unbroken state. Entropy, a measure of disorder, almost always increases because higher entropy configurations are overwhelmingly more likely. Thus, irreversibility emerges not from the laws themselves, but from the sheer statistics of large numbers. Isn't it fascinating that what feels like an absolute law is really a matter of overwhelming odds? A lesser-known fact is that at very small scales, reversals sometimes do occur. In carefully controlled experiments with microscopic particles, researchers have observed rare fluctuations where entropy briefly decreases as if the arrow of time hiccups. But these moments vanish quickly, drowned out when billions of particles are involved. This suggests that irreversibility is not a fundamental law, but an emergent phenomenon, fragile at small scales, robust at large ones. Could it be that the arrow of time is not written into the fabric of the universe, but is instead a byproduct of size and complexity? The paradox is striking. Physics, at its core, is reversible, yet our lived world is irreversibly one-directional. Out of timeless laws emerges the flow of time we all experience. The mystery is whether this arrow is only a statistical illusion or whether it hints at something deeper, perhaps tied to the universe's birth in a low-entropy state at the Big Bang. Why, after all, did the cosmos begin in such extraordinary order, setting the stage for time to unfold? And so we are left with a haunting thought. Is time's arrow an inherent property of reality, or only a shadow cast by the improbable starting point of our universe? At the atomic and molecular level, the fundamental equations of motion are time-symmetric. Newton's laws, Schrödinger's equation, and even Maxwell's equations work identically whether time flows forward or backward. If we reversed all particle velocities in a system, the system would retrace its past states. Exactly. This reversibility suggests that time has no intrinsic arrow in microscopic physics. In principle, nothing forbids the movie of atomic motion from being played in reverse. Yet this microscopic symmetry clashes with our macroscopic experience of time's one-way flow. This reveals a disconnect between theory and perception that physics must explain. The paradox begins with the contrast between reversible laws and irreversible reality. Simulations of colliding billiard balls look the same whether run forward or backward in time. Realize it is like watching ripples on a pond. Played in reverse, the motion still looks physically plausible. At human scales, processes clearly unfold in only one direction. A broken glass never reassembles itself spontaneously, and aging progresses only forward. Heat flows from hot to cold, not the reverse, and smoke disperses but does not recollect into its source. These phenomena define the arrow of time in daily life, making irreversibility seem obvious and universal. Our practical experience reinforces the belief that time must flow in one direction. Yet when reduced to microscopic components, no single particle forbids reversal. This dissonance between experience and microscopic law lies at the heart of the paradox. Why irreversibility dominates our lives, despite reversible rules, is one of science's great mysteries. Ice melts naturally into water, but water at room temperature never freezes spontaneously back into ice. It is like eggs, scrambling easily, but never unscrambling themselves. The arrow of time is explained statistically by the second law of thermodynamics, which states that entropy tends to increase in isolated systems. Entropy measures the number of microscopic configurations consistent with a macroscopic state. Low entropy states are rare and ordered, while high entropy states are common and disordered. Over time, systems almost always evolve toward more probable high entropy states. This statistical inevitability explains why macroscopic processes are irreversible. Even though microscopic laws allow reversibility, entropy makes reversal practically impossible. Thus, entropy provides the bridge between reversible dynamics and irreversible phenomena. Time's arrow is statistical rather than mechanical. A gas spreads evenly in a container because that state corresponds to vastly more microstates than a localized one. It is like shuffling a deck of cards. There are countless random orders, but only a few that look arranged. The arrow of time also depends on how the universe began. Cosmology suggests that the early universe after the Big Bang was in a remarkably low entropy state. This improbable starting condition set the direction for entropy's steady increase over billions of years. The universe evolves from order toward disorder because it began in an unusually ordered configuration. Without this special beginning, no clear arrow of time would exist. The cosmic origin explains why we see entropy increase rather than decrease. This dependence on initial conditions reveals the arrow of time is not inevitable, but contingent. Our experience of irreversibility is therefore a legacy of the Big Bang. The smooth distribution of matter in the early universe was highly ordered and set the arrow of time in motion. It is like starting a ball at the top of a hill. The slope ensures it rolls in one direction. On very small scales, entropy can fluctuate downward temporarily, creating brief reversals. Such fluctuations are rare, but theoretically possible in systems with only a few particles. At larger scales, with billions of particles, however, the probability of reversal becomes astronomically small. Statistical averaging ensures entropy almost always increases overall. This explains why irreversibility dominates in our world, despite microscopic reversibility. The arrow of time is thus not absolute, but emerges statistically. It is overwhelmingly likely rather than strictly required. The bigger the system, the sharper the arrow of time. In principle, air molecules in a room could all cluster in one corner, but the probability is effectively zero. It is like tossing a coin a billion times. The chance of getting all heads exists, but is unimaginably tiny. Quantum mechanics adds another layer to the paradox of time. The Schrödinger equation is perfectly reversible, but measurement collapses the wave function irreversibly. This collapse introduces asymmetry, linking time's arrow to the act of observation. Some interpretations argue that decoherence with the environment, rather than collapse itself, produces the appearance of irreversibility. Decoherence spreads entanglement so widely that interference becomes impossible to observe. Thus, quantum measurements embed irreversibility into macroscopic outcomes. The transition from reversibility to irreversibility may occur at the boundary between micro and macro. Quantum mechanics therefore ties the arrow of time to information and observation. In the double-slit experiment, observing which slit the particle goes through destroys the interference pattern irreversibly. It is like opening a book of possibilities, but being forced to choose a single page permanently. In biology, irreversibility is deeply connected to energy flow and entropy. Cells maintain order only by consuming energy and exporting disorder to their surroundings. Metabolism is an irreversible process that transforms low-entropy fuel into high-entropy waste and heat. Aging also reflects entropy's march as molecular damage accumulates in organisms. Life survives by creating local order but accelerates entropy globally. Biological processes therefore depend on time's arrow. Without irreversibility, evolution and memory could not exist. Biology mirrors thermodynamics in every heartbeat and breath. Organisms burn food to maintain internal order but release heat, increasing entropy overall. It is like building a sandcastle while the tide rises. You create temporary order while disorder grows around you. Our experience of time is psychological as well as physical. We remember the past but not the future, linking consciousness directly to irreversibility. Memory formation requires entropy increase since recording information leaves physical traces. Our sense of forward flow is anchored in these irreversible processes of encoding and recall. Thus, perception itself is asymmetrical, tuned to the universe's thermodynamic arrow. We cannot imagine time running backward because our cognition is built on irreversible changes. Human experience therefore reflects rather than defines the arrow of time. What we call the flow of time is a construct of entropy and memory. Writing notes records information permanently about the past, but never about the future. It is like footprints in sand. You see where you've been, but ahead lies only untouched ground. The paradox is that microscopic physics is reversible, yet macroscopic life is ruled by irreversibility. The arrow of time emerges statistically from entropy, cosmologically from initial conditions, and practically from measurement and observation. What appears symmetric in theory becomes asymmetric in reality. Time has no built-in direction at its foundations, yet entropy gives it one. Certainty of irreversibility emerges from underlying reversibility. The arrow of time is thus both real and emergent, illusion and fact. Reconciling microscopic symmetry with macroscopic direction remains one of physics' deepest unsolved questions. Time's arrow reveals how laws and lived experience can diverge, yet still be connected. Breaking a glass is irreversible in our world, though in theory, reversing every atom's motion could restore it. It is like a reversible script, performed only forward. The words could be read backward, but the play always advances.